Hi, welcome to Extra Maths. Today we're going to deal with exponents and logs, and in fact you will see that a lot of the work in exponents you have already done. But I decided that it was a good idea for us to start there, because if your exponents are solid, then your logs will be solid as well. So we're going to first recap a lot of grade 11 work. So the topic is exponents and logarithms, and I would like to start by talking about surds, which are very much a part of your exponents. So let's go over here and see what I'm on about. Now surds, if we've got the square root of 9, that would not be a surd because we know that the square root of 9 is just 3. But if I take the square root of 12, then it would be a surd. Now how do we do that? Well, in grade 8 we learned a method where we used to use ladder. And we used to take the number 12 and break it down into its prime factors. So let's quickly go and look at how we used to do that. But before we do that, let's recap what I mean by a prime number. A prime number is a number that has exactly 2 factors, 1 and itself. If it has more than 2 factors, we call it a composite number. And let's have a look at some of these numbers. If we looked at the number 1, well, 1 only has itself as a factor. So it doesn't have 2 factors, so it's not prime and it's not composite. The number 2, the only factors we can get for that are 1 and 2 itself. So 2 falls into the prime factor section. If we take the number 3, well, 3 is divisible by 1 and by 3, and if you look there, that's 1 in itself, so it's satisfying that condition, so 3 is also prime. But now we take the number 4. Now 4 is divisible by 1, by 2, and by 4. So it's 1 in itself and another factor, so that means that falls into the composite numbers. 5, well 5 would be 1 and itself 5, and so therefore that would be a prime number. 6 would definitely be composite. So we take 6, the factors would be 1, 2, 3, and 6 itself. So that would fall here. And this is how we would categorize them. So I mean, this is pretty basic stuff. You know this from when you were in grade 8. I'm sure the teachers drilled this into you. Well, now the reason why is that we always go for prime factors when we're working with exponents, because they always make our life easier when we actually get to simplify it. So let's have a look how we're going to do this. I don't think we need this definition here anymore, so let's take that off. And let's start with your grade 8 method. Grade 8 method, we would take the 12 like this, and we'd say, what is the smallest prime that will divide into 12? Now the smallest prime is 2. And if a number is even, then it's certainly going to divide by 2. So we would take 2 into that, and 2 would go into 12 6 times. This is still even, so I can divide by 2 again, giving me 3, and now it's not even. The next prime number up is 3, and we're going to get 1. So this is equal to the square root of 2 times 2 times 3. Now, in grade 8, you learned that for every 2 in a square root sign, you take 1 out. So it will become 2 root 3. And that is definitely a surd. Now, you can imagine the bigger the numbers get, the more awkward it gets to do this process with a ladder. So we need to come up with a more effective way, although there's nothing wrong with using the ladder method. And the most effective way to do it is to take your primes and dividing them in 1 by 1, try and get the other thing to be a perfect square. So let's have a look at it. If I take the number 12, 1 is a perfect square, but 1 is not a composite, so let's try 2. If I divide 2 into 12, I will get 6. Neither of those are perfect squares. 3 is the next prime, and 3 will go into there 4 times. Now that is a happy occasion because 4 is a perfect square. So instead of writing root 12, I can write the root of 3 times 4, which is equal to the root of 4 times the root of 3. The root of 4 being 2 root 3. And you can see that's quite an easy way to get that answer. Now I'm going to spend a time doing an example with you just now, but I just want you to try and get this little start because it just makes life a lot easier. The good news is that some of our calculators do this for us automatically. But if I was a teacher, I would say show all working or something like that to make sure that you understood what to do. So let's pull the calculator up and just show you that that's how it works. If we look over here, I want to go root 12. Doing that, I hit the equal sign and look at that. It's 2 root 3. Exactly what I got using that other method. So it's quite useful to know that. I can get that simply either using the ladder method, using this method, or of course our friend the calculator. Either way we can get around the problem. I want to stop for a few seconds and talk about some laws of surds. And it's really relatively easy. I'm just going to run through a few of them and then we're going to get into the question I've got here just to refresh your memories. So let's talk about our laws. The first one says, if I have the nth root of a times the nth root of b, it is equal to the nth root of ab. Notice this had to be the nth root and that had to be the nth root in order to do this. This is quite a useful rule. Let me show you an example of it. So for example, say I've got the root of 2 times the root of 8. Now root of 2 can go nowhere. Root of 8 could simplify using our methods, but if I did this rule, I could say it's the root of 2 times 8, which is same as saying the root of 16, which is going to be 4. How much easier is that than doing the other method? Of course, the other method is absolutely fine, but it's worth knowing those rules. Right, the second rule that's quite useful is if I have the nth root of a over the nth root of b, and I'm dividing, and they both have nth roots, I can make it the nth root of a over b. Again, a very useful question. Something like this would be a nice example of it. Let's say the square root of 8 divided by the square root of 2. Well, according to my rule, I can make that the square root of 8 divided by 2, which is the square root of 4, which is 2. So yes, it could have some uses. Let's show you one more rule of it, just to remind you, in fact, maybe more than one more rule. I'd like to also bring in some other stuff here. If I have the nth root of a mth rooted, then I could just as well go the nth root of a. So I could make it one sign by multiplying those together. Now that looks scary, but let's just quickly talk about one other rule that will make sense to you. Do you agree with me when you were doing exponents last year, you learned that the nth root of a to the m is the same as saying a to the m over n. And of course, we'll recap that shortly. So if I'm using this principle on this particular question, I could say to myself, this is the same as saying the mth root of a to the 1 over n. And then I could say to myself, that is the same as saying a to the 1 over m. Oops, sorry, I put the square root sign in, so let's just take that out. I could say that is equal to a to the 1 over mn, and then unraveling it into this form again, I can see I would get that answer. But it's much easier to see it in number form, and it makes much more sense to you then. So let's just take that out, and let's find an example where this would be a good idea. Let's say, for example, I say to you, let's find the cube root of the square root of 64. Now, of course, let's just take this other rule out here because it'll just be in the way while we're working with this. If we wanted to, there's absolutely nothing wrong starting on the inside and working out. Now, you'll see I've written there square root. I don't have to do that. Do you agree? That square root can be there or not be there. If there's nothing written, we immediately assume it's a square root. So using this principle, we could say this is the cube root, and the square root of 64 is going to be 8. 8 times 8 is 64. And the cube root of 8 is going to be 2. So it works out very nicely like that. But I also could say it's the 6th root of 64. Now if I do that, 64 is the same as saying 2 to the power 6. And then using this exponential law that this becomes this, I could then say to myself, well, that means that's 2 to the 6 over 6, which is actually 2 to the 1. So sometimes these rules will be useful to you. However, I want to rather concentrate on how we would get asked this in an exam. We could be asked these like almost academic kind of questions, but more likely not. Let's move to the example. Right, let's move across to the question and have a look at it. It says here in the question, simplify without the use of a calculator. So without the use of a calculator, that is important. Show or working, so they're stressing. So yes, we can cheat with a calculator, but we need to show all our working. Now I'm going to do it without the calculator because it is quite possible. And then I'm going to show you that if we did use the calculator, we would end up with the same end product. Right, if we look at this here, it says root 50 plus root 36 minus root 8 all over 6 root 2. So the first thing I'd have to do is make these surds into the simplest form. So if I start with a root of 50, in fact, let's bring it over a little bit so it's clearer to see. I'm going to do it in the middle of the working and then we can always tidy up later. So let's look at the root of 50. Remember what I said to you? We take the 50 and we say, right, let's break it up into a prime times something. Now the smallest prime that will go into 50 is 2. And do you agree with me that 50 is 2 times 25? 25 is a perfect square. So instead of writing root 50, I could go 25 times 2. Right, let's move to the next one. Root 36. Well, root 36 is just a normal square root. The root of 36 is 6. So there's no surd involved here at all. So we're just going to go plus 6. And this one over here is minus root 8. Remember what I said to you? We take the number 8 and we say, what's the smallest prime to divide in there? And 2 will divide into 8. So we could write this as 4 times 2. So we'd write this as the square root of 4 times 2. Over, well, this one's already simplified, 6 root 2. Right, let's take that away and we're ready to work. Right, now remember what I said to you, that means the same as saying root 25 times root 2 plus 6 minus root 4 times root 2 using my rule over 6 root 2. You do not need to show this step. Okay, I'm putting it in there, but in actual fact you can go straight to the next step without showing that, so don't worry about it too much. So let's have a look at it. Right, so on this one now I could say root of 25 is 5 root 2 plus 6 minus, and that thing's going to be 2 root 2 over 6 root 2. Right, now what we need to understand is these root 2's are like variables in the sense that they're the same kind of animal. So if I'd had an expression 5x plus 6 minus 2x over 6x, you would have had no problem dealing with that. You would have just said, well, 5 minus 2 is 3x plus 6 over 6x, and you would have gone on from there. Okay, so all we're going to do is exactly that. We're going to say we are going to treat these root 2's like they are variables, and we can add them up and divide by them and all sorts of exciting things. So let's go back there. 5 root 2 minus 2 root 2 is going to give me 3 root 2 plus the 6 that was there over 6 root 2. Now the question is, are we finished? And the answer is no. You can already see I put the equal sign there, which sort of gave it away. But in actual fact, we are not finished because we can now simplify this using our basic fraction knowledge. So let's go back to the question. Now if I go over here, I see that I've got a common factor. If I'd had 3x plus 6 over 6x, you would have immediately said to me, well, let's take out the 3, giving me x plus 2. And over here I would have 6x. That would go once, that would go twice. Well, the same thing's going to happen here. So I'm going to take out the 3, leaving myself with root 2 plus 2 over 6 root 2. That goes once, that goes twice, and my answer is root 2 plus 2 over 2 root 2. Are we finished? Well, it depends what the question was about. and it also depends what your teacher wants. Most people would accept this without rationalizing, but I think it's an important time to revise this whole principle of rationalizing. What we do here is we say it's never all right to have a square root sign in the bottom of a fraction. Why? Well, a square root sign on a non-perfect square is a non-terminating, non-recurring decimal, being irrational. Now, is it possible to take something non-recurring, non-terminating, and divide into something? Well, no, it's not. It's easier to have that unknowns thing at the top and a real, definite number at the bottom, because it's possible to take something solid and give an answer to so many decimal places. So what we do is we rationalize. Now, rationalizing is actually multiplying by a convenient form of 1. So if I look at this, 2 root 2, if I times by root 2 over root 2, that is the same as timesing by 1, just written in a different form. You agree? Now, obviously it doesn't pay to cancel that out, because then I'm back to where I started. So what I do instead is I say, let's multiply that in here. So I'm going to say root 2 times root 2, which of course gives me root 4. I'm going to write these steps, but in actual fact you can avoid them. This is 2 root 2 if I times in here. And at the bottom here I've got 2 root 4. Right, now still looking at this, I can see that root 4 is actually 2 plus 2 root 2. And at the bottom here, that's going to be 2 times 2. Right, which is not bad at all, because now I can see that that 2 can come out as a common factor, giving me 1 plus root 2. And at the bottom here, I've got 4. And if I look at that, I can say 2 goes into there once and 2 goes into there twice. And so my answer is 1 plus root 2 over 2. Now, do you agree with me? That's a really nice answer there. However, I would not do this unless the teacher or something was said to me, give your answer with rational denominator, or your teacher stressed it in class or whatever, because you could have been happy to stop at this stage rather than that stage. Now, let's go up and go back to the question and show how the calculator would have made my life a little bit easier. Well, not a little bit easier, actually quite a lot easier. So let's put it on the side here. And let's erase this here, and let's, in fact, I'm just thinking if I should pull it down more. Yes, I think I should. Okay, so let's go and get the calculator. There it is. And let's clear it. And now we can say to ourselves we want the root of 50. So all I would do is I would go root 50 equals. And you can see there's my 5 root 2 coming out immediately. So over here I can go 5 root 2 plus, well, hopefully we don't need a calculator for that. It's 6 minus. Pull up the calculator again. We've got the root of 8. So we're going to go root 8 equals, and we get 2 root 2. Okay, at the bottom we've got 6 root 2. And you see that we've jumped right here immediately. The rest of the question will work exactly like before. Oops, gone a little bit too far. And so it wouldn't really matter. You know, the way the teachers think generally is if we can do it mentally, then we expect that you can do it mentally as well. And so we would look at this and say to ourselves, we can do this in our heads, and so the pupil can too, and we would give you the benefit of the doubt. All right, let's move across to exponents and quickly recap your exponent rules, and we can go from there. Let's go to exponents. Right. Over here, we've got exponents, and I'm going to quickly go through each of your rules to remind you how they worked. The first rule said to me, if I have a to the m times a to the n. Now notice, the bases are the same, and I'm multiplying. So that would be equal to a to the m plus n. So when we are multiplying, the bases are the same, we add the exponents. Now please remember that this rule can work this way or that way. That's why there's an equal sign. It means you can go this way or that way. Right, the second rule says to me, if I have a to the m divided by a to the n, it's equal to. Now what's it equal to? Well, if we're dividing, we can subtract the exponents. So we'd write the a down, and we would go m minus n. Okay, and then the third rule says if I have a times b to the power n, then it's equal to a to the n, b to the n. Just before I move off this one, I just want to mention that if we're breaking this up, we could also write it as a to the m times a to the minus n. And you're going to see me do that quite often on this rule. But in effect, it means the same as that because remember, negative exponent is 1 over, and we're going to get to that rule in a moment. Right, the fourth rule says to me, let's just get it up a little bit, if I have a to the m all to the n, well then it's equal to a to the m times n. In other words, if I am raising to a power, I multiply my exponents. Right, a fifth rule says to me that if I have a to a negative exponent, it is equivalent to 1 over a to the positive exponent. And that fits in with what I was telling you here. In other words, this would become a to the m times 1 over a to the n, which then becomes a to the m over a to the n. So it all fits in around that. Right, the sixth rule we need to know about is that a to the naught equals 1. Right, and now I've added one of my own rules, which I found very, very useful in lots of problems that we come across. Let's go to it. Number 7. It says if we have a over b to the negative n, it's equal to b over a to the plus n. Let's explain why that works. Let's start on the left-hand side. Let's get ourselves some space. This will become 1 over a over b to the n. Now, if I'm going to do the rules on this, I could say that's 1 over a to the n, b to the n, which is equal to 1 times, and the rule says we invert and multiply this one, so it becomes this. And as you can see, this is now going to be b over a to the plus n, which is precisely what I got on the right-hand side. Right, so that is basically the rules, and you can see that's useful, and you'll see me use some of this, especially number 7. I'm really very fond of my own rule. Let's go now and look at a question and see how it was done. Right, it says, question 2, simplify the following. Now, very important is whenever you get these exponential questions, the first thing you do is you ask yourself, does this only have and this is quite important, multiplying, dividing, raising to powers, or rooting? You don't have to have all of them, but some of them. Well, let's look. It's raising to powers, it's multiplying, it's dividing, and it's raising to powers. So yes, if I'm going to look at what I've got here, I've got multiplication, raising to powers, and dividing. So yes, it follows that category. Now, the moment I see that, the good news is I know I can use my exponential laws to simplify that I don't need to do anything strange or unusual. It's just straightforward use of rules. So let's see how this was done. First thing I would do is I would look at this and I'd say, okay, fine, let's prime our numbers. Well, 2 is already prime, so I'm going to leave it just as it is, as 2 to the x minus 1 times 3 to the x plus 1, because that's also prime. But 6 is not prime. So 6 would be 3 times 2, and I would raise it to the power x plus 2. Now notice that if I look at this, this now can split up. Remember my rule, a, b to the n is a to the n, b to the n. So let's use it. So it's 2 to the x minus 1 times 3 to the x plus 1. And this now, using my rule, will become 3 to the x plus 2 times 2 to the x plus 2. So that's a straight application of this particular rule. Okay, now we look at it. And we can see the good news is we again have a rule that's coming in here. We know that if we have a to the m over a to the n, it's equal to a to the m minus n. And if we look over here, we've got a 2 to a power and a 2 to a power. Notice we must have the same base, otherwise we're in trouble. So doing that, we can do that. So we can write down the 2. And the rule says we can subtract the exponents. So we are going to go x minus 1 subtract x plus 2. Right, now we've got a base 3 here and a base 3 here. So we can go along here. Let's make it pink. Put a 3 over there. And we take the top exponent, subtract the bottom exponent. Right, now you can see at this moment it looks hideous, but don't worry because you're also welcome to miss this step. Obviously, I would suggest that if you're not sure or you're feeling that you could be making careless errors, it's always better to show more steps than less steps. It helps your examiner to see where you might have gone wrong and then to follow through on your incorrect working. So it gives them method mark opportunities. So it's never a bad idea to show more steps. You also don't want to overkill it, so you want some fair sort of division between it. So let's go back to the question. Right, so in the blue, I'm going to put down the 2, and I know this is going to be x minus 1 minus x minus 2. How did that work? Well, there's a little invisible 1 there that we times in there and in there. Of course, I could have gone straight here just by saying top exponent minus bottom exponent. Then we go to the 3's. We put the 3 down. And again, I'm going to get rid of the brackets. So it's x plus 1. Remember the little invisible 1. We're going to times it in there. So it's minus x minus 2. Right, so over here we've got 2. Minus x plus x falls away, and that's going to be minus 3. And then we're going to put down our 3, and we see that the plus x minus x falls away, and that's a minus 1. So basically, we've improved the situation in that we don't have any x's anymore. However, it's never all right to leave negative exponents in these questions. So what you're going to do now is you're going to use the rule that says a to the minus n is 1 over a to the plus n. So all I'm going to do is I'm going to make this happen. I'm going to put a 1 at the top because both of these are negative exponents. And I'm going to bring this to the bottom and this to the bottom. And of course, that's the same as saying 1 over 8 times 3, which is 1 over 24. And there we have our answer for this expression. And actually, I always marvel at mathematics because we look up to this hideous little question we had over there, and we think, how on earth did it end up with such a nice number like 1 over 24? But that's the beauty of mathematics, that it can take something quite complicated and just simplify it into really a nice number. So that's great. Let's move on to the next question. Now you can see this next question, I've made it a little bit more complicated than it was on the first one. And you can see that this is going to take a little bit more on your priming activities. So let's go and look at it. We've got 100. Now yes, 100 is equal to 10 squared. But 10 is not a prime, so the object of the exercise is, if possible, to write it as the product of primes. So we take the 100 and we say 2 would divide into their 50, 2 would divide into their 25, 5 would go into their 5, and 5 would go into their 1s. So 100 is replaceable with 2 squared times 5 squared. And we've still got it to the power minus n over 4. Right, now 15 can also prime. So if we take 15 and we put it on the side, we do our little ladder thing. 2 won't go, but 3 will go 5 times, and 5 will go once. And so we can write that as 3 times 5, all to the power n over 2 plus 2. Right, the next one we're going to do is we're going to do 24. So let's get purple going. So that one's 24. So we take 24 on the side. Smallest prime in there is 2. 2 goes into their 12. 2 goes into their 6. 2 goes into their 3. And 3 goes into their 1. So we can write this as 2 cubed times 3, all to the power n over 6, or exponent n over 6. Right, that leaves me with one more to find, which is this 9 over here. And 9 is 3 squared. I don't think we need to worry about that too much. And it's, let me write that in black so you remember that is the exponent that was there earlier on. Right, and the exponent was n over 3 plus 1. Right, now it looks like we haven't improved the situation at all, but in actual fact we have. Original question had 100, 15, 24 and 9, and this question only has 2, 3 and 5. So having 4 numbers, we've brought it down to only 3 numbers, which is going to make it more simple to simplify. Right, so using our rule, we know that this exponent here must multiply onto this and multiply onto this. So the pink one is going to become 2, and 2 times that is going to be minus n over 2. 5 minus n over 2. So look what I'm doing. I'm saying 2 times minus n over 4. That goes once, that goes twice. It's going to give me minus n over 2. So it's a straightforward calculation. Right over here, this is going to be 3 to the n over 2 plus 2 times 5 to the n over 2 plus 2. And this purple one is going to be 2, and if we multiply those, n over 6 times 3 means that that'll become n over 2. And this one will stay 3 n over 6. And at the bottom here, we're going to change to the blue pen. It's going to be 3, and now the bad news is that doesn't cancel, so I'm going to get 2n over 3 plus 2. Remember, that 2 will affect this one and that one. This is a big area of making mistakes. People are inclined to forget to multiply this 2 onto that and onto that. So make a point of it, and if you need to do these little lines to remind yourself, then please do it. Okay, so right, now what are we going to do? We're going to take them one by one and deal with them. And this time I'm going to use a shorter method of doing it rather than showing you all the steps, and I'm going to take them one at a time. So let's write down the 2, and we know it's going to be minus n over 2. Now over here is a 2, and over here is a 2. We are multiplying them, so we add on this exponent. Remember, the rule says a to the m times a to the n is a to the m plus n, just adding straight forward. So that takes care of my 2's. Right, let's put the 5 down. Now we've got a 5 there, a 5 there. So we're going to go minus n over 2, and then we're going to add to that n over 2 plus 2. Now things are starting to look a little bit better. I'm sure you're starting to see that if you look over here, that's actually going to take that one out, and that one's going to take that one out. So already I've got rid of some of these n's that are floating around. Right, let's now look at our 3's. Put down the 3, we can see there's a base 3 there, and a base 3 there, and a base 3 there. It's a very good idea to underline them as you go, because then you know if you've got them all. It's very easy to forget one when you've got so many to collect. So what are we doing here? We are adding. So we're saying n over 2 plus 2 plus n over 6. But then we are subtracting, and I'm actually going to put that in black so you can see it. Subtract. This is going to become 2n over 3 minus 2, because both of those signs have got to change if I'm subtracting. Right, let's start from here now, and we can see here that that minus n over 2 plus n over 2 falls away, so I'm going to get 2 to the 0. And then in the blue, I can put the 5 there. That and that fall away, so I'm going to end up just with a 2. And then I'm going to get the 3, and nice news is that and that fall away. And here, if we add this up, we're going to do a little sum. So we're going to say we have n over 2 plus n over 6 minus 2n over 3. Let's take a common denominator of 6. 2 goes into there 3 times. 3 times n is 3n. 6 goes into there 1, so that's going to be plus n. 3 goes into there twice, and that's going to be minus 4n. And look at that. Isn't that wonderful news? Because it's 4n minus 4n over 6, which means 0 over 6, which means that is actually a 0. So even though that looked so complicated, it wasn't that bad at all. Now we go over here. What do we know about 2 to the 0? It's equivalent to 1. What do we know about 5 squared? It's 25. And what do we know about 3 to the 0? It's 1. And if we times that whole lot out, we get 25. Now, isn't it amazing that something that looked so hideous can come out to such a nice little answer, just like the previous one? Right, let's look at the next kind of question. But before we do that, let's just quickly recap a little bit. Remember, I said to you, if we have multiplying, dividing, raising to a power, and rooting, we just use our rules. Very important to note here at this stage is we never split exponents at this kind of question. Now you'll say, what is that? Well, you're about to find out when we go to the next kind of question, where I do split exponents, and I'll show you how to recognize and identify that. Let's go to the next question. This question says, simplify the following. Now you'll say to me, well, hang on, that doesn't look that different to the previous one. But in actual fact it is. Let's show you why. Do you see what we've got here? In the previous question, we had no adding and subtracting in the base. So this time we have adding and subtracting in the base. We also have multiplication. So it's going to be a combination of two things here. So let's give ourselves some notes. If we have a plus or a minus in the base. Now, before we go any further, let's just recap what I mean by that. The base is this part. The exponent is this part. The whole thing is called a power. So here, this plus sign is on the base and not up here, which is in the exponent. Then, as soon as we see that, we split exponents. Now, what do I mean by split exponents? What I mean is you reverse your rules. So if it was a to the m plus n, I'm going to write a to the m times a to the n. If it was a to the m minus n, I'm going to write it as a to the m times a to the minus n. So right, let's do that. Over here, I have 3 times 2 to the x times 2 to the 1. At the bottom here, that's just 2 to the x. I've got my add sign, and that's going to be 2 to the x times 2 to the minus 1. Now you might say, well, what are you doing? This is making it look worse. Well, yes, it does partly, but it gives us a way to carry on. Now, if we look at the question again, you can see that 2 to the x and 2 to the x is in both of these terms, which means I can take it out as a common factor. So at the moment, I've got that 3 times 2 to the x times 2 to the 1. And here at the bottom, I can say, let's take out this 2 to the x as a common factor. Now, if I do that, I'm left with 1 plus 2 to the minus 1. Now, you might say to me, well, how did that help things? Just let's remind you about good old algebra here. Do you agree if I gave you something like that? You could take out the x and leave yourself with 1 plus 3. Because here there's a 1 in front, so when you take the x comes out. So here, if we take out the 2 to the x, there is a 1 here. That is very important. You cannot afford to get that incorrect. Remember, if you're taking out the whole thing, there is a 1 left in your factorization. Okay, so let's have a look what we can do. We can say that 2 to the x divides into that 2 to the x. Now, I know what some of you are thinking. You're saying, really, why could we not have just done this? Let's just have a look. Why couldn't I have said that? Well, that is an illegal mathematical operation. Let's explain to you why. If I've got 3 times 4 times 2, and at the bottom I've got 4 plus 4 times 2. If I do that, it's completely incorrect. Let's show you why. If I didn't do that cancelling, 3 times 4 is 12, 12 times 2 is 24. At the bottom I would have 4 plus 8. So that would give me 24 over 12, which would be 2. Now over here, if I cancel like this, I'm going to get 3 times 2, and hopefully you would have realized that's 1 plus 8, which is going to be 6 over 9, which is 2/3, which is clearly incorrect. So please remember, we can never ever do that. So I'm just going to take that out because that's a huge mistake that people make, and it's very easy to do that mistake, by the way. So just be aware of it and be careful not to do it. Right, so that's where we were and that's what we had, and we're about to go from here. So at the top, what we've got left is 3 times 2, which is 6, and at the bottom we've got 1 plus. Now remember what I said to you, never leave a negative exponent, so it's 1 plus a half. Now once we're here, we can say that's 6. Now if we add 1 to a half, we're going to get 1 1/2, which could be written as 3 over 2. You can, of course, use your calculator to help yourselves out here, but I think that's easy enough arithmetic. So that's 6 times, and we can invert and multiply this to 2/3. So doing that, we're going to get that goes once and that goes twice, and the answer is going to be 4. Right, it's relatively straightforward. Let's look at a more complicated version of this. As I said, this is just revision of last year's work, so I'm going relatively quickly because I just want to recap what we learned. Right, next question. It says simplify the following, and they give you this. Now, what do we notice immediately? We notice that we have plus signs in the base. That means we're dealing with a similar kind of thing to the previous one. Now, what we need to do is keep this nth root running. 10, we know, can break down to 5 times 2. So we could write this as 5 to the n times 2 to the n, plus, this is going to be 2 to the n times 2 to the 2. Underneath, we've got 5 to the 2n plus 4 times 5 to the n. Now, what does 5 to the 2n mean? Well, it means this. It means 5 to the n all squared, or we could think of it as 5 to the n times 5 to the n. I personally think we're better off thinking of it like that. Let's see what happens next. Now, if I look at the top of this fraction, I can see that there's a 2 to the n there and a 2 to the n there, which means I could take it out as a common factor. So let's get our nth root going. At the top, I can take out 2 to the n, leaving me with 5 to the n plus 2 squared. Now remember what I said about this. I said that is the same as saying 5 to the n times 5 to the n. So let's replace it with that. At the bottom, I have a 5 to the n as a common factor. So let's take that out. 5 to the n. What's left? I'm left with a 5 to the n plus 4. Now, what do we know about 2 squared? Well, hopefully we know that 2 squared is actually 4. So we can write this like this. And now we can see that we can take this and divide this into this. Remember, we can cancel or divide out when the whole bracket is the same, but the whole bracket must go. I can't take parts of the bracket. It must be the entire bracket that cancels. So right, this gives me the nth root of 2 to the n, 5 to the n. Now, from our law of exponents, we know that if we have the nth root of a to the m, the rule says it's a to the m over n. So this is going to become 2 to the n over n divided by 5 to the n over n, which means this answer is going to be 2 to the 1 over 5 to the 1, or if you like, just 2/5. So once again, something quite complicated becoming something relatively straightforward. Right, let's move on. Now this next one appears like it's something different to what we were doing. And in actual fact, it is partly. Because yes, it involves exponents. But in actual fact, this becomes algebra when all is said and done. But we are going to use our basis. But please notice, once again, we've got minus and plus signs in the base. So it's not our straightforward laws. It's going to be involving something else. All right, so let's see what happens with this one. I think I took that up a little bit too high, so let's just bring it down. Now over here, I see I've got a negative exponent. So the first thing I'm going to do is I'm going to go m minus 1 over m. Now at the bottom here, I've got a square, which means I've got m to the half plus m to the minus a half times m to the half plus m to the minus half. I'm doing this deliberately because this helps you to see that in actual fact, we're going to times our firsts, then we're going to times our outers, then our inners, and then our lasts. So at the top, we've still got m minus 1 over m. And at the bottom, we're going to do this first outers, inners, lasts. So let's do that. So m to the half times n to the half. This can get confusing. So it's worth a little quick mention. The bases are the same, so we put it down, and we add our exponents, which means we get m to the 1. Now, I know a lot of you would have thought to yourself, well, it's going to be m to the quarter. And the reason being is because we normally just times those together. But in actual fact, with exponents, we're not. We're adding. So be careful. That is the exponent we're busy working with. Right, back to the question. And then we're going to times that by that. So this is m to the half times m to the minus a half using the same principle. It's a half minus a half, which is m to the naught. So that's m to the naught. This one over here is also m to the naught. And this one, only difference is going to have negatives, so we're going to have that happening. So it works out to be m to the minus 1. Right, now things are looking a little bit simpler than it was looking. So let's have a look at what we're going to do next. So let's go over here. And we can see here that we could take a common denominator of m. That's over 1. So 1 goes into there m times, so it's m squared minus 1. At the bottom, we can maybe tidy up a little bit. So we've got m. What do we know about m to the naught? Well, we know anything to the naught is 1. So it'll be 1 plus 1, which is 2, plus, and that's a negative exponent, so we're going to make it 1 over m. Now, I'm sure at this stage you realize that in actual fact this is just an algebraic question where you're simplifying a fraction. So it's not exponents anymore. You did have to use exponents to do that foiling, and you had to use your exponents to work out your negative exponent. But really, other than that, it's just a straightforward algebra question. So let's carry on. Right, so we have m squared minus 1 over m all over. Now this one we're also going to put over a common denominator. 1 goes into their m times m is m squared. 1 goes into their m times, that's going to be 2m. And m goes into their 1, so it's going to be 1. Now we've got what we call a double-layered fraction or a compound fraction. Now that can be complicated, but it's actually very easy. All you've got to remember is we take the top fraction and we multiply by the inverted bottom fraction. Now just to make it a little bit easier, I'm going to write it in a different way for you so you can understand what I'm doing. So here I've got m squared minus 1 over m, and I'm going to divide by m squared plus 2m plus 1 over m. Looking at that, we can say that is m squared minus 1 over m times by m over m squared plus 2m plus 1. Same principle as if I just inverted that. All right, now what do we have to do next? I'm sure you remember me always, well, I don't know if I've done this with you, but I love an expression. It goes like this. It stands for factorize the flipping fraction. So let's factorize the flipping fraction. Let's take that and let's go m minus 1, m plus 1 over m times by m, and if we factorize this one, it's m plus 1, m plus 1. Now looking at that, I can cancel that m with that m. I can take that m plus 1 with that m plus 1, and my answer is m minus 1 over m plus 1. And that's the end of this question. So as I said to you, it's a straightforward simplifying a fraction. In actual fact, it's got really very little to do with our exponents. So right, let's move on to the next question and see what that says. All right, now you can see we're moving into our equations. The question is saying to me, solve for x. Now with these, again, there are two kinds you need to worry about, and they work along the same lines as the other. We check, do we have multiplying, dividing, raising to powers, or rooting only? And the answer is clearly yes. Look there, we've got raising to powers. In fact, that's all we've got. So what we would do in this case is we would try to, well, not try, we will prime our bases. Now hopefully, and I almost think this is worth knowing, it's worth knowing to a certain point what powers to learn. So you should know that 4 is 2 squared, and you also should know that 8 is 2 cubed. This way it just makes our life so much easier if we've got that knowledge. Otherwise you have to do those ladders, which are not the end of the world, but they take some time. And over here, 8 is 2 cubed, and that's going to be raised to the power 3x minus 5. Right, now using our rules that say a to the m all to the n is equal to a to the mn, we can now multiply those. So we're going to go 2 to the 4x equals 2, and we can times there, we're going to get 9x minus 15. Right, now at this stage, we can see we've got a base 2 here and a base 2 here. Now I'm sure you remember when you were in primary school, you would have seen questions probably like this where they said to you, fill in the missing block. And basically what they wanted you to understand is if the equal sign was used, then everything had to be absolutely equivalent on both sides of the equal sign. So going to this question that you would have got in primary school, you would have looked at this and said, well, it's equal, that's a base 2 and that's a base 2. So the only way for that to happen is for there to have been a 2 in that block. So we're using a similar kind of thinking, and we're saying, therefore, because the base 2's are the same and there's an equal sign, 4x equals 9x minus 15. It's called equating exponents. So now we can just solve this. So we can say 15 equals 9x minus 4x. So 5x is equal to 15. Divide this side by 5 and this side by 5, and x is equal to 3. There we are. Question finished. Relatively straightforward. Now, I'm going to skim a little bit on the next few questions because the next one is very similar. It's got a little bit of a twist, which we need to just talk about, but I will put it in the extra questions to be done with the solution, so you will be able to go back and look at that at your own leisure. This one looks like this. Now you can see it's sort of got a similar format, but it's got a little bit of a complication in that this is quite long-winded. And really that is just numbers. So let's see if we work just with the numbers, what happens. Well, we have 2 to the 4, which hopefully you know is 16, plus 3 times 4 squared is 16, and here we got 3 times 64. Tidying that up, I've got 16 plus 48 plus, and 3 times this is 2, carry the 1, 192. So if I take 192, add 48 and add 16, I'm going to get 6, carry the 1, that's 10, that's 5, 256. Now, if you know your powers, you will know that 256 is a power of 2. So after having simplified that, I get something that is a straightforward power of 2, and I'm back to the same kind of question as the previous one. So as I say, I'm not going to carry on working that question out, but I just wanted to show you that sometimes you need to work a little bit before you make a decision about what type of question this is. Right, moving on to the next one. Now, this one is different because if you look here, we have a minus in the base. Remember the story with that. And remember how it worked? If we have a plus or minus in the base, we split exponents. So right, let's have a look at that. So 2 to the x minus 2 to the x times 2 to the minus 1 equals 8. Now if you look at it, it's not quite as easy as those previous ones we were doing where you just take out a common factor and they cancel out and life becomes easy. This you have to do a little bit of thinking, and there are 2 methods that are generally used. And I'm going to use both, and you can decide for yourself which one you prefer. This one here, you'd look at it and you say, okay, have I got my x's on one side of the equation? And the answer is yes, I do. And I see that this and this are like terms. And so we could take them out as a common factor. So if I take it out, I'm left with 1 minus 2 to the minus 1 equals 8. Now this bracket can be simplified. So this becomes 1 minus a half equals 8. So 2 to the x, well, 1 minus a half is a half equals 8. And we can divide this side by a half and this side by a half. So 2 to the x equals 8 times 2 over 1, because remember we invert and multiply, that falls away. So we have 2 to the x equals 16. And of course 16 is a power of 2. It's 2 to the 4, and therefore x is equal to 4. So that is the one approach to it, and it's absolutely fine to do it like that. But there's another one that is quite useful, especially if you're someone who gets a bit confused with this section. Let's show it to you. Let's go up to the top again. And what this does is it says, let us do a substitution. Let k equal 2 to the x. So I'll go over here, in place of that orange splodge, I'm going to put k minus k times 2 to the minus 1 equals 8. So it's going to be k minus. Now remember, a negative exponent drops to the bottom as a positive exponent. Now if I look at that, I can see that's a normal algebraic expression. And so what I would do now is I would eliminate my denominator, because we don't like working with fractions. So I'm going to times the whole thing through by 2. Doing that, I'm going to get 2k minus k equals 16, which means k equals 16. But k was 2 to the x. So 2 to the x equals 16. 2 to the x equals 2 to the 4. And therefore, x is 4. A little nicer, a little kinder than working with all the different layers of exponents. So it's really your own call on that, and you can decide for yourself which one you prefer. Right, next question. Well, not even a next question. We're now moving on to our logarithms. Now, this is the actual grade 12 work. And I want to spend a few minutes, I have mentioned it in other sessions, on how a log relates to an exponent. But it's worth doing this again because this is the crux of everything. So let's quickly recap that. What we learned previously in sessions is that if we have log to the base a of b equals c, it is possible to bring this into the form of a to the c equals b. That's the base, That's the exponent, that's the number. So writing it in words, log to the base. Now notice how I write my base under the g's tail. That way it avoids confusion of a number equals an exponent. And so in terms of that, I would say base to the exponent equals the number. Right, now we need to stop for a few seconds and just talk about restrictions on these various things, because this becomes very important when we start working with our logs. If I look over here, this base, remembering that it's actually going to be this a value, we say it is always greater than 0 and it's never equal to 1. Now, why would we put that restriction on it? Well, if the a was negative, so say it was -2, do you agree with me? It would depend if I was raising to an even power or an odd power. Even power would make it positive, odd power would make it negative, so it would be all over the place. So mathematicians are very practical. What we do is we say, let's eliminate issues that don't make this work or conform regularly. So we just say, okay, we're not going to work with a base that is negative. So that's our first restriction. These become very important later on, and I will refer back to it. Right, the next restriction is, if you look over here, the number itself. If we've made the base positive, what do we know about this number? Well, the number, or if you like the b value, must also be greater than 0, always. Because if we've got a base that's positive, no matter what we do to it, our answer will be positive. So if I look over here, I can see that that's going to be the case no matter what. So if that's a +3 to some exponent, that would be a positive. So we know that. The last one we've got to look at is the actual exponent. Now, an exponent, do you agree with me? That could be absolutely anything. It could be fraction, it could be irrational, it could be whole, it could be negative, it could be absolutely anything it wants to. So the good news is that the exponent, or the c value, is absolutely anything. It's an element of reals. Now, basically, the log laws are going to work exactly like your exponent laws. And I'm going to go through them all with you. I must just encourage you at the moment and tell you that in actual fact, this section, logs, used to be a huge section of the previous syllabus. Your syllabus, however, it is a relatively small section. All we have to be able to do is use it to solve problems. That's really the absolute essential part of this, is you have to be able to solve problems using logs. But what I'm going to do is go a little bit deeper than that in case the examiner decides to go a little bit more theoretical. But it's not as hectic as it used to be in the previous syllabus, so that's good news. So don't be afraid of the section. It's a very small portion of your work. Right, let's have a look at what I mean by the rules, or the laws. Okay, law number 1 says, if I have log to the base a of b, c, then I can make that log to the base a of b plus log to the base a of c. Now that ties in directly with our exponential laws. We know that when we're multiplying numbers in exponents, we add the exponents. So if the bases are the same, we add the exponent. Well, same thing here. If the bases are the same and we're adding, we multiply the numbers. Now that makes perfect sense. Number 2, if I have log to the base a of b over c. Now when we were doing exponents and we were dividing, what did we do to our exponents? We subtracted them. Well, the same thing is going to happen here. We are going to subtract the logs. So that is equal to log to the base a of b minus log to the base a of c. Right, third law. If I have log to the base a of a to the m, in fact, let's make it b to the m. We don't want to use the same letter. We are raising to a power. What do we know from our exponents? When we raised to a power, we actually multiplied the exponents. So the same thing is going to happen here. We're going to get m log to the base a of b. Okay, and you can see that's the multiplication, if you like, of that, which is the exponent, by the m. Right, there is a fourth rule And again, it's become not really that essential to know, in that you've got calculators that work with different bases. But I'm going to show it to you just in case we need it somewhere along the line. It's not very hard. It starts over here and it says, if I have log to the base a of b, and for some odd reason, I need to change my base from base a to base x, say, then what I would do is I would say it's log to the base x of b divided by log to the base x of a. Either way, it's going to work out much the same. Right, now we have a few deductions we need to work with as well. So let's have a look at those. The first deduction says that if I have log to the base a of a, so in other words, the base and the number agree, the answer will be 1. This makes perfect sense because this base goes to that exponent. Now, a to the 1 makes a. So it's perfect. Right, number 6. We have log to the base a of 1. Now, if that happens, that a must go to the power 0 or 0 in order to get the 1. You can see it clearly. A to the 0 equals 1. This was a to the 1 equals a. So that's worthwhile knowing. And then there's one of my own again. As I say, they just come in really handy when you've got them. It says if we have log to the 1 over a of b, it is equivalent to minus log to the base a of b. Not so useful here, but very useful when we get to our graphs. So I'm going to stop it off there because at a later stage we will be spending some time with our log graphs and exponential graphs. So I don't want to go into too much detail on that, but let's go and look at the questions we get. Right, this first question looks as follows. Now, what I want you to realize is when we look at a log question, and it says simplify without a calculator, let's just highlight that. They really do mean that. And if you use the calculator, you're not going to get any marks. So they want to see the kinds of rules you are using to get out. The first thing I would do is I would check my bases. So I have base 2, base 2, base 2. So they're all the same kind of animal. So that means I can use my laws. So let's go along here and we can say that is equal to. Now, we know from our rules that adding means multiplying. So I would go, in fact, let's make it black so you know what I'm doing, log to the base 2. And because of this add, I'm going to go 12 times 5. Because of this subtract, I'm going to divide by 7, 5. Okay, so notice the adding means I multiplied the numbers. The subtracting means I divided. I could do this because they all had the same base. That is very important. So it's equal to log to the base 2. If we look over here, this would be 60 over 7, 5. And I'm going to be very good today and not use the calculator. So that's 7.5. 7.5 will be 15 over 2. This is going to be log to the base 2, 60 times 2 over 15. Remember the rule is you invert the bottom fraction. And this then, the 15 goes once and into there 4 times, becomes log to the base 2 of 8. Now it appears like you're finished, but the bad news is well, not the bad news, the good news is you're not. Remember we had a law that said log to the base a of a is 1. And 8 is a power of 2. So we can go log to the base 2 and make 8 2 cubed. Now, we're using the rule that says log to the base a of b to the m is m log to the base a of b. So we're going to take this 3 here and bring it to the front. So we're going to go 3, and then we're going to write the rest of it log to the base 2 of 2. From this rule, I can say that is the same as saying 3 times 1, which is 3. And that brings us to the end of that question. Very nice little question. Let's move on. This one, again, a similar kind of question, but do you see this time? We have the same base in 2 of them and another base in 2 of them. So if I go to my pens here and I highlight, this has got a base 3 and this has got a Oh, I haven't. There are actually 3 different bases. There's a base 3, a base 2, and in fact, there is also a base 10. Now, what I haven't mentioned yet, and I'm going to quickly mention now, if we write down log 5, it actually means log to the base 10 of 5. We never write that base 10. It's just a convention. It's like when we write an x, we never write the 1 in front. If we do, we do. If we don't, we don't. But it's better not to because we're actually wasting ink. And it's a convention and understanding we all have about that. So there's no problem with that. We can leave it as it is. So right, let's go over here and take that away and let's start looking. Right, so let's start with the log to the base 3 of 27. We know that 27 can be written as 3 cubed. Now remember that story, this power can go in front, so I can put it in front and I can leave the rest of it here. Just to make it more obvious, that 3 has gone in front there. The others have stayed exactly where they were. Now the same can happen here. This is log to the base 2, and 8 is the same as saying 2 cubed. This 3 can come in front here. So we can say minus 3 log to the base 2 of 2. And now remember I said to you that this one over here is actually a base 10. So what I'm going to do is I'm actually going to write the base in. It's totally unnecessary to do that, but let's do it so we understand. Now, what I'm going to do is I'm going to put this in a bracket. So I'm going to say log to the base 10 of 5 plus log to the base 10 of 2. Remember that that minus out there, we change that to a minus up there. So it's minus. And over here, I'm going to go log to the base 10. And adding means multiply. 5 times 2 is 10. Let's write it in so you don't forget. Right, so going over here to our purple one, we have 3, and we know from our deduction that's equal to 1. We've got the minus 3, and from our deduction we know that that is 1. And then our pink one, we've got minus log to the base 10 of 10, which as you know is 1. So we have 3 minus 3 minus 1, which means my answer is minus 1. So just notice that if the bases are all different, then I have no choice but to do that. Right, next question. This one here, simplify without a calculator, this expression. And here we have a choice of going about it in several ways. I'm going to just do one of the ways. You could, of course, use your rules, which get a little bit complicated, or you can just prime your numbers and sort out from there. So I'm going to go that route. So I'm going to say 27 is the same as saying 3 to the 3. 125 is the same as saying 5 cubed. And 9 is the same as saying 3 squared. And 25 is the same as saying 5 squared. Right, from our laws, we know that this exponent can come in front. Remember, there's that rule. You can see it quite clearly. All of those can go in front. So we have 3 log 3 minus 3 log 5 over 2 log 3 minus 2 log 5. And hopefully at this stage you're looking at it and saying to yourself, well, this doesn't look so bad anymore. This looks actually doable. So over here we're going to take out our 3 as a common factor, leaving me log 3 minus log 5. Just to emphasize it, I'm taking that out as a common factor and that out as a common factor. And underneath here I'm going to take out a 2 and I'm left with log 3 minus log 5. Now notice the brackets are identical, which enables me to cancel, and my answer is 3 over 2. Good, so that brings me to the end of that question. Let's see what's next. This is another simplify, and I'm actually going to skip this one out and put it in your exercises to do because it's much the same thing. Just one thing I want to remark about it, and that is that this here would be done first. The bracket would be done first. Okay, so you would first tidy that up, and then we would deal with everything else over there. So it's a good one to practice on. I'm going to leave that one for you to try. Right, this one as well, again, very nice question, and I'm going to again put it in your sheet, but I just want to show you one thing again about this. If I'm going to, in fact, you know what, I'm going to do this one. This one I think is worth, it's a bit different. So let's do it. Let's get ourselves a pen. This one says simplify without a calculator, and this time We see that all the bases are p, which is good. But more importantly, we're going to simplify a whole string of things. We're going to try and condense it. So let's have a look at this. We're going to write down our log base p of 12. We see that this thing can come back as an exponent. So I can go plus log to the base p of 5 squared minus log to the base p of 3 minus, and this can come back as an exponent again, log to the base p of 10 squared. Now, our bases are all the same, and we can see that these are rules. So we're going to do that. We're going to write down log to the base p. Remember what I said to you. If we're adding, it's multiplying. So there's adding. So I'm going to go 12 times 5 squared, which is 25. And at the bottom, these are subtracting. So we're going to put them at the bottom. 3 times 10 squared. Right, so we have log to the base p. Let's just get this up a little bit. 12 times 25 is going to be 300, I hope. I'll check it in a moment. And this is 3 times 100, which is also 300. Let's just make sure about that. 12 times 25. If we're working without a calculator, the easiest way to do it is to say, well, that's 3 times 4 times 25. That gives me 100. Yes, and 300 is right. So right, what we're going to do now is we're going to say that's log to the base p of 1. And of course, that's one of our deductions. We know the answer is going to be 0. Right, let's move on to the next example. And this time we get to the real purpose behind why they teach us logs. They are asking me to solve for x. Now, before we were looking at things like this, we were looking at something like this, which was not problematic because all we had to do is write this to the power 3. So it was easy to do. Now this one, there's no way I can make 5 a power of 3 easily. So what I'm going to do is I'm going to use my log definition. So let's go to this log definition and talk about it. So if we have a to the b equals c, then we know that log to the base a of c equals b. So let's talk about it. That base, if you like, kicks that up to give you that. So that goes up as the exponent, and that's your answer. So we're unraveling this. So we're going to go log. What is the base of this exponent? It's 3. What's the number? The number is 5. And the answer we're going to get is x. And now it would just be a matter of inputting that into my calculator. So let's get the calculator up. Let's clear it. And we're now going to put it in. Now you might notice there are 2 buttons. There's this button where we can see the 2 things together. And that's the one we're going to use. So we're going to put 3 in there. And we're going to put 5 in there. And then we're going to press equals. So we find that x is equal to 1,46. And in fact, let's just pull it up to get any more places. 464. So that's good enough for now. It won't change 2 places. Now, what have we actually done? What we've done is we've said 3 to the 1,46 blah blah fish paste is equal to 5. Let's see if that's true. Pull up the calculator again. What we're going to do is we're going to take 3 and we're going to raise it to the answer and see what we get. Yes. Obviously, if I use the rounded off answer, I'm not going to get exact answers. So let's just do that to show you. If I went 3 raised to the power 1.46, you can see I get 4,9727. If you round it off, you're going to get 5. So yes, that does work. Okay, so relatively straightforward, not a problem. How would we differ then with something like this? Well, the only difference is we've got a 2 in front. So the first thing we would do is we'd eliminate the 2 by dividing both sides by it. So we get 3 to the x equals 5, and then we're back to that same question. So just remember that. You must first divide and then you get it. There is another way to do it as well. And it really is your choice. What you could have done is you could have said, let's log this side and let's log this side. If we do that, that's an exponent, so it can come in front. And we can now divide this side by log 3 as long as I divide this side by log 3. So x is equal to log 5 over log 3. Pulling our calculator up, you can see that this would give you exactly the same answer. This time, however, we would use the other log button. So we would go log 5. Of course, we would close our brackets, divided by log 3. Close our brackets. And you can see the answer is identical for these two, so it makes no difference. So it's 1,46, blah, 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 blah. Okay, so that takes us through that. So let's look at one more example. And then I'm going to probably have to leave it at this stage and pick it up when we go to look at our graphs, because we need to go a little further into our logs to finish up the section. Now, they say solve for x. Now, before you even start this, think back to our restrictions. Our restrictions were the following. They said the first thing we do is we look over here, and this is a base. Now, what do we know about this base? We know that x would have to be greater than 0, and x would not equal 1. And we must always bear this in mind when we are solving. It depends where they put that x as to where we would have to do that. Right, so what we're doing here is we're looking at this, and what we're going to do is that method I've shown you now, where we say the x kicks that up to give me that. So x kicks up the 1,5 to give me 125. Right, now to solve that, we can write this as x to the 3 over 2, because 1,5 as a fraction is 3 over 2, is 125. How do we undo this? Well, the first thing we're going to do is we're going to raise this to the 2 as long as we raise this to the 2. So we're going to get x cubed equals. Now this is the same as saying 5 cubed. So we're going to get x cubed equals 5 to the 6. Now, to get rid of that cube, we cube root this side as long as we cube root this side. So x is equal to 5 to the 6 divided by 3, which is 5 squared, which means x is 25. What we do at this stage is we glance back and we say, is there going to be any problem with that particular restriction? And no, 25 is bigger than 0 and it's not equal to 1. So we are absolutely fine with our definition. So we are quite happy with this as it stands, and we know that that is the right answer. Now, if we went back and we put it in the calculator, we'll see that that actually is true. So let's just check that on the calculator just to make ourselves complete. So I'm saying log to the base 25 of 125 equals 3 over 2. Let's see if that's true. Pull up the calculator, clear it. We're going to use this button. We're going to put 25 in there. We're going to put 125 in there. We're going to press equals, and there you go. You can see exactly what I'm saying, that it's 3 over 2. So that's a nice way of solving it. Remember how conscious I was of those restrictions. So we are going to stop here, but we need to go a little bit further with this work, and we will do it before we go and look at the more on the exponential and log graphs, because there's a whole lot of work on that. So thank you for joining us today, and I hope you've enjoyed the lesson and you've got a bit enthused as to how logs are going to help your life, and we will carry on with this when I next pick up this topic. Many thanks. Bye-bye.